Okay, so this lecture is moving on and still discussing one-way independent samples ANOVA, but this lecture is particularly for computation and application. How to apply one-way ANOVA and how to compute one-way ANOVA. So again, we're going to compute and apply one-way independent samples ANOVA in this lecture. So independent samples ANOVA, just to recap, one-way independent samples ANOVA compares means of two or more independent samples, right? So again, it analyzes the variance between the mean scores, examines variability both within and between groups. So to calculate this, we have several steps. One, we need to state the null and research hypotheses. By this time in the quarter, you should begin to understand that this is going to be sort of a standard part of computation of most of our statistical procedures, stating the null and research hypotheses. Defining the critical region, this is also something that's come up several times. Computing the test statistic, in this case it's the F-statistic. And computing the effect size and describing it, and then summarizing the results. And so we'll go through each one of these steps independently. So let's give the example that we gave in the conceptual lecture. Mars is interested in launching a new color for their M&M's line. To do so, they are going to experiment with three colors, pink, purple, and light tan, to identify which color is most attractive to consumers. To see which color is most attractive, Mars places consumers in one of three rooms, the pink, purple, and light tan rooms, respectively. Each has a bowl of pink, purple, or light tan colored M&Ms. Right? So participants have an option to eat these M&Ms if they wanted to. So to measure M&M color attractiveness, they simply count the number of M&Ms eaten for each participant. So here's our little table here, right? So each one of these cells represents a different person, and then each one of these overall groups represents a group, right? So the first person in group 1 was the pink group. That person ate 25 M&Ms, right? And that varies from looks like from 9 up to 25. So there's variation here. And the average for that group, the average number of M&Ms eaten is 16.3. Purple group here, same sort of thing. Average here was 8 M&Ms eaten per group, and then the light tan group had an average of 15.5. So the question we're trying to answer when we're running a one-way ANOVA is, do these groups significantly differ with regard to the number of M&Ms eaten? And so we'll figure that out. So there are several elements we need to identify here. First is the number of groups, right? Here there are 3 groups, so G equals 3 in this case. And this is important to note because we'll be using G quite a bit. And then N, we all know N, and N is simply the number of scores across the group. So N here is just the number of people who participated in this particular study, right? So we have 6 people per group. That gives us 18 people in total. So first what we need to do is state the null and research hypotheses. The null hypothesis in this case always states that the means are equal, right? So the null hypothesis in a one-way ANOVA is going to be relatively similar. So in this case it's going to say there were not significant differences in the number of M&Ms eaten across the 3 color conditions. So remember, we're trying to identify whether there are significant differences across those colors, whether some colors are more attractive to eat than other colors. Our research hypothesis, on the other hand, in this case, we're stating at least one group was significantly different from another group. So in this case, at least one M&M color was eaten more than at least another M&M color. And we don't have to specify which is which, right? This is we can be exploratory in this and just try to figure it out and let the numbers tell us. Step 2, we need to define the critical region. Now the critical region here is similar to defining the critical region with the t-test, right? So we're going to use degrees of freedom in this case. In t-test, where we only used 1 degree of freedom, in ANOVA, we're going to be using 2 degrees of freedom because we're looking at the groups and we're looking at the individuals within those groups. So we need the degrees of freedom between, that means the degrees of freedom between groups, right? And that is calculated by the equation G minus 1. So again, G is the number of groups in the independent variable. In this case, it's our 3 groups, right? Our pink, purple, and light tan. So our degrees of freedom for the between groups is G minus 1 equals 3 minus 1, which equals 2, right? 3 groups minus 1 is 2. We also need to find the df of the within, and this is n minus g, where n is the number of scores or people in the study across all the groups. So not within the groups, but across all groups. So in this case, we have 18 minus 3 because we have 18 people and we have 3 groups. That gives us a degrees of freedom of 15. And what we do is we open our appendix C. So our degrees of freedom between, we're going to use as our numerator, and because we have a 2 here, we're going to look up the 2. Here's the numerator here. The degrees of freedom within, we're going to use as our df denominator. And so crossing these two, this column and this row, we're going to get our overall degrees of freedom, which is 3.68. So note that this is the critical region. We need to figure out if our F value scores beyond this critical region, either plus or minus 3.86. And remember, just like t-tests and just like with z-scores, if it's beyond the critical region, then we know that it's significant. We know that there are significant differences between groups. So step 3, compute this test statistic, or the F-statistic. So there are 4 steps to this, and we need to complete this entire F table. Now, oftentimes your sums of squares will be given to you, in this case by me. In real life, it's not, and this is one of the reasons why we use something like SPSS. Because we can enter the data, and SPSS will give us this entire table very quickly and easily without us having to compute it by hand. Even with a small number of scores, this can become overwhelming very quickly. We will compute this by hand today, but in the future we're going to be looking at something like SPSS to compute these types of scores. So to begin with, we want to compute the sum of squares, and we want to start with the sums of squares between groups. Okay, so we're looking at these particular numbers here. So I'm going to condense this table into something a little more visually easy to read. And so I just transpose this table. So we have our means for the pink group and our means squared for the pink group. And so what we'll do is we'll use some formulas to calculate our mean squared, our sum of squares. And so our sum of squares for the mean is calculated by this equation here, which is sigma mean squared, or the sum of the mean squared scores. So that's this number here, times the sum of the mean scores squared, divided by the number of groups, right? And so we plug these numbers in here. So this mean squared is we get that from squaring this number times itself, right? So 16.33 squared is going to equal 266.7767, and that's where we get this number. Then we sum all of those numbers and we plug them in here. So the sum of the means equals 39.83. We plug that in here. Sum of the means squared is 571.0267. We stick that in the front of the equation. We calculate these numbers out, and what we get is 42.129. And so that'll give us our mean squared between groups, or part of our mean squared between groups. That's the sum of squares of the mean. So to get our SS between, we calculate the sum of the squares of the mean times this little n. And so the difference between the little n and the big N, the little n is the number of people within each group. So in our case, we have 6 people within each group, so our little n is going to be 6. So we have our 42.129 times 6. That gives us 252.78. That's a lot of numbers. Just understand that you need to plug in your mean squared and your sum of the mean squared and your sum of the means into these two numbers here, as well as the number of groups, and that'll give you the calculations that you need. So now, and so that's for specifically for the between groups. Now we need to calculate the sum of squared for the within groups. So just to focus on one group, we have to do this for every single group. So I'm going to do this for just one group, and this is what I'm talking about. This is how you can see this can become fairly overwhelming. So I'm going to calculate this for one group and ignore the other two. I'll have the numbers there. If you want to compute them yourself, go for it. Just for the sake of time, I'm only going to do one group. So what we have to do is, you'll probably remember back in terms of calculating standard deviations, right? This is a similar process. So we need to first calculate deviation scores for every single person within the group. So the deviation score is the person's score, or X, minus the mean, right? So that would give us the deviation scores. Then we need to square those deviation scores, and that'll give us our all positive integer numbers, right? And then we need to sum each of those scores. And so that'll give us the sum of the square deviation scores. So we need to do this for every single group, right? So this is why it can become overwhelming. So we have our sum of squares. So I did this already for group 1. This is the same thing for group 2. Same thing for group 3. They're obviously different numbers because there are different scores. So what we do is, to do the sum of scores within, we simply add those 3 numbers up. So our final score is 308.83. Then to calculate the total sum of squares, we simply put together, or we add the sum of squares between plus the sum of squares within. So we have our sum of squares between, sum of squares within, and that gives us 561.61. And we'll input that information into our data table. Now the rest of our data table is fairly straightforward to compute because we have these numbers now, right? We have the degrees of freedom. I'll put them in here in a second, and I'll show you again how to calculate those. The mean squared falls from those two numbers, and the F-statistic falls from the mean squared and the sum of squares, right? Just the mean squared itself, as well as the effect size. So all of these sort of follow, so it's important to get the sum of squares correct as well as degrees of freedom correct. So again, let's find the degrees of freedom. We did this a little bit earlier, so I'm just going to run through this quickly. So we have our between groups degrees of freedom is 2. Within groups, degrees of freedom is 15, and our total is those two put together. It's not those two put together. It's the overall N, or the sample size, minus 1. So again, we have 2, 15, and 17. So I'll just plug those numbers in. So now we need to compute the mean squared. So the mean squared is the sum of squares between groups divided by the degrees of freedom. So we take these numbers, sum of squares between groups, divided by the degrees of freedom. That gives us 0.39. We do the same thing for the within groups, except we use the within groups row, right? That gives us 20.59. Plug those numbers in. Now we need to calculate the F-statistic. The F-statistic is the mean squared of between divided by the mean squared within. So let's go back to the conceptualization of this. Remember, we're figuring out the variance of the mean squares, we're trying to figure out the difference in groups by calculating the variance, right? And if you go back to that conceptual, the conceptual equation, this is what the conceptual equation is. It's the mean squares between divided by the mean squares of within. And that gives us a 6.14. And remember, this is greater than the critical value that we found a little bit earlier of 3.68. So this is telling us that there is a significant difference between the groups, right? So there is something going on there. And to figure out exactly what's going on there, we can compute Tukey's honestly significant difference test. And so what this does is that identifies the differences for each group compared to every other group. And HSD is calculated with this equation here, where Q is, and that's found in Appendix D, uses the number of groups and degrees of freedom. So if you look in Appendix D, you can use those two numbers and figure out your Q value. Times the square root of the mean squared within divided by our little n, and again, remember our little n is 6. So when we plug in our numbers, our Q, I found it in the book, is 3.67, and we calculate these numbers. That gives us our HSD of 6.80. So what does this mean? What does this HSD of 6.80 mean? What that means is that we're identifying whether the raw difference between each mean of each group is beyond this. If there are differences between groups, so if group 1, if the absolute mean difference in group 1 is greater than this, if the absolute difference between group 1 and group 2 in terms of their means is greater than this, then we can say there's a significant difference between those groups. So you'll see what I mean. So if we look at this, if we do a comparison 1, here are the means here, right? So 16.33 minus 8 is 8.33. If that 8.33 is greater than our HSD score of 6.8, then we do have a significant difference for that group. That's very important to note. So we calculate these numbers out using the means, and we find that pink is greater than purple significantly. Purple is greater than, in this case, light tan is greater than purple, significantly greater than purple, but there's no difference between light tan and pink, right? So now we need to compute the effect size. So the effect size is called eta squared, or partial eta squared is what it's called. That's the statistics for it. You can just call it eta, ETA, that's fine. And it's computed with the calculation here. So again, we have all of this data in the table. We can plug in the numbers. So the sums of squares between divided by the sums of squares between plus the sums of squares within. So this says sums of squares error. And because it's within groups, the error is identifying that the measurement error as well as the individual differences. That's what the error is referring to. So whenever you see something like this that says error, it's always referring to the within groups, okay? Especially with one-way ANOVA. So we do the calculations here, and we come up with a value of 0.45. And we compare that to the table. So this is not the same as the Cohen's D, right? It's not the same as the Cohen's significance. This one's different. This one's slightly different. So it's not quite as large as the Cohen's. So its large value goes up to 0.25. And as we can see, this is quite a bit greater than 0.25. So we can say that this is a fairly large effect. So we need to summarize the results. To summarize, we need our F-statistic, our degrees of freedom, and our F-statistic is 6.14, our degrees of freedom for between and within groups, our p-value, our effect size, our mean squared of the error, or that's the within groups mean squared, the means and the standard deviations of the groups for the post-hoc comparisons. And when you summarize the results, this is very important. It's going to look something like this. So the summary basically gives us a breakdown of what we did, what we found, what was significant, so on and so forth. And so you'll see something like this, or you should be able to write something like this. In independent samples, ANOVA with 3 groups was conducted to test the color of M&Ms on the consumption of M&Ms. A significant effect was found. F in parentheses 2,15, so this refers to the between groups degrees of freedom. This refers to the within groups degrees of freedom. This is the score that we got, the F value. So we have all of our data here. This is the p-value, or the alpha level, right? So the probability value. This is our partial eta squared, so our effect size. And this is the mean squared of the error. TUKEY post-hoc comparisons revealed that people who were given pink M&Ms consumed significantly more than those who were given purple M&Ms. And we report the values here. And these are our post-hoc comparisons, right? That TUKEY test that we conducted. Additionally, those given light tan M&Ms also consumed significantly more than those who were given purple M&Ms. So this summary basically is telling us that there are significant differences with regard to the color of M&Ms. And that's an important piece, right? That's telling us that if Mars, for example, wants to introduce a new color of M&M, it would be best to introduce either a pink M&M or a light tan M&M. Those two were eaten the most frequently based on our data. So what I want to do is I want to give you a practice problem. So you want to know whether IAS students differ in the number of genres of music they listen to compared to other students. So we'll call this variable student type. You have the following data table, right? So you have the raw data for each of these. So this is the number of genres people listen to within each of these groups, right? So you need to calculate the mean, the standard deviation, so on and so forth. And here is the final answers. So use the data in the data table to compute all of this data within this table. Sums of squares included, degrees of freedom, mean squared, F value, so on and so forth.